MOSAiC, which I'm sure many of you have heard of, but Matt's going to frame it as how MOSAiC fits into the larger Arctic Observing Network. So, Matt, whenever you're ready, and Jessica has your slides up, please feel free to take it away.
Okay, just want to confirm you can all hear me and see the slides.
We can.
Very good. All right, well, thank you. My name is Matthew Shupe at the University of Colorado in Boulder, and Jeremy initially asked me to speak about MOSAiC, and I kind of suggested that maybe many of you have already heard the MOSAiC spiel, and so then we agreed that maybe it's better to talk about how MOSAiC integrates with the rest of the kind of broader Arctic observing system. And so that's going to be more of my focus today. But MOSAiC is the multidisciplinary drifting observatory for the study of Arctic climate. And I have a few slides where I'll kind of say what it is for those of you that don't know yet. But mostly I'll try to focus more on some of the bigger picture here. And I just wanted to start out with putting up a list here of some perhaps important Central Arctic science questions. And I'm just going to read through some of these. These are some of the questions that motivate me and I think motivate a lot of us that do Central Arctic kind of research. So what are some of the driving mechanisms for the decadal sea ice decline? Can we forecast sea ice on scales of days to decades? What is the energy budget of the Central Arctic surface and the Central Arctic system? How does change in the coupled system impact things like biological cycles? How do changes in the Central Arctic system kind of predispose that system for further changes? So feedback's happening on kind of interseasonal and interannual scales. How good are satellite products for Central Arctic processes and properties? Things like sea ice, atmospheric structure, clouds, energy budgets. How well do large-scale models and reanalyses perform in the Central Arctic for things like momentum transfer, surface energy budget, clouds? And can we develop operational coupled system models with skill at representing that coupled system and coupled system processes and their change in time? So these are just some questions, and of course there are many more that motivate our work in the Central Arctic. And I would argue that for a lot of these questions, our ability to answer them is kind of limited by a limited amount of observations in the Central Arctic environment, in that sea ice in the Central Arctic Basin. And, you know, the IPCC kind of agrees with that. This is just a quote from IPCC Report suggesting that, you know, our understanding of polar climates is incomplete because that the system is complex there. It's coupled atmosphere, land, cryosphere, ocean, ecosystems interacting together. And there are a lot of feedbacks. But importantly, the serious problem that they know here is a lack of observations against which to assess models and to develop our process knowledge. And some of the important things that are listed here at the bottom that are causing the biases that we see in, for example, simulating sea ice are things like high latitude winds, vertical and horizontal mixing in the ocean, surface heat flux errors, atmospheric boundary layer structure, and high latitude clouds. So our ability to answer some of the important questions is limited here by observations. And so I would say, on the whole, the Arctic observing system has some insufficiencies. This is not to say that it's all bad. Obviously, we do a lot of great things with the Arctic observing system, and we make a lot of great measurements. But there are some important gaps that I think it's important for us as a community to really acknowledge and understand. So we have key lacks, key deficiencies, if you will, in the Central Arctic especially. And in particular, you know, I'm an atmospheric scientist, and we really lack measurements of the atmosphere in the Central Arctic. So things like clouds, aerosols, surface energy budget. We lack the kind of long-term perspective of how these manifest in the Central Arctic system. And our observing has a warm season bias often. You know, we go out there and do intensive campaigns, or we fly aircraft, or we do a variety of activities, and often these are more biased towards the summertime season when it's easier to get into the Central Arctic and easier to make the measurements. And then my last point on this slide is that from the perspective of coupled system measurements, we really don't do that very well anywhere. I think there's a lot of observing activities that we have where we tackle certain parts of the coupled system. You know, some of the buoy clusters that are drifting through the Arctic right now, I think, do a good job of, for example, understanding the interface of the ocean and the sea ice, but lack a lot of the atmospheric perspective, for example. And so I think that, again, here's a major insufficiency of the Arctic observing system is the coupled system perspective. So I want to move to thinking about and contemplating the challenge of sea ice prediction. This is really one of the motivators for MOSAiC, and I think it's really important for us to consider as, you know, everyone, if you will, is interested in sea ice. And maybe everyone's kind of loose there, but certainly a whole lot of U.S. agencies, the public sector and private sector, a lot of communities, for example, and of course a lot of international partners here. A lot of people are very interested in sea ice prediction. And so let's think about that for a little bit. And, you know, when we're thinking about sea ice prediction, physics really matter. To make improvements in our model representations, we actually have to do a better job of representing the physics. And actually, you know, I was just at AGU, and I was actually astounded at how often I heard that message. I think it's a really important message for us to understand. To understand sea ice, you have to know the thermodynamics and the dynamics. And these things occur year-round. It's not just a summertime phenomenon where we're looking at how thermodynamics and dynamics impact sea ice. And coupled processes really matter. So the ice is an integrator of both the thermodynamics and the dynamics in the system, of how the atmosphere and the ocean they're constantly forcing the sea ice and moving it around or changing its temperature, for example. So we really have to understand these coupled system processes. And we have to also understand the intraseasonal coupling. So there's a growing appreciation of how, for example, radiative effects in the spring are preconditioning that sea ice and really driving what's going to happen with it in the fall and the sea ice minimum. And of course, the ice is changing, and so our reference state is changing. So how do we represent physics in a system that's evolving? That's really important to consider. So these and some of the deficiencies I listed before are really some of the motivating factors for MOSAiC. And I'm going to provide here just a few slides to give an overview of MOSAiC. I won't belabor it too much because a lot of you I know have heard some of this. But MOSAiC is a drifting interdisciplinary process study in the Central Arctic. And there's basically three parts for MOSAiC, and I've listed them here. The first part is a central observatory, and that observatory is going to be the polar stern icebreaker. The Germans have offered this to drift in the sea ice for a full year. So that central observatory is going to serve as the base of operations for the project. On the ship and near the ship, we're going to have very intensive observations in the atmosphere, in the sea ice, in the ocean, and in the ecosystem, all done together in a coupled way. And so that platform, that ship's going to be frozen into the sea ice in the fall of 2019, somewhere in the kind of northern part of the East Siberian Sea. And it's going to be set to drift for a full year. And that's going to go somewhere along the transpolar drift, kind of what I've suggested by that red arrow in the plot. The second part of the MOSAiC plan is to have a distributed network of measurements around that central drifting observatory. So this distributed network would be with autonomous sensors, with unmanned aircraft or underwater vehicles, providing context around that drifting facility on model grid box scales, so tens up to perhaps 50-kilometer scales around that ship. Capture heterogeneity and important coupled system processes. The third part is coordinated multi-scale analysis and modeling activities. So this is ranging from very detailed, process or large eddy simulation model studies that really pull in the very detailed observations and scaling up to regional scales and hemispheric scales. A lot of this analysis and modeling activity will be done in coordination with the Year of Polar Prediction, which I think a lot of you know about, and I'm not going to go into detail about right here. But it's a large international activity that's bringing enhanced observations and a lot of modeling activities to the Central Arctic on the same time frame. So those are the three basic parts of MOSAiC. The science drivers are listed here. These are based on a series of workshops we've had over the past many years, at least 5. So the leading science question is, what are the causes and consequences of an evolving and diminished Arctic sea ice cover? So we see sea ice here is at the heart of this activity. We're interested in the processes that are leading to that evolving sea ice cover, but also the impacts that it's having on the system. So I've listed here 5 sub-elements, if you will. These are getting more specific in terms of the kind of processes that we want to study, and there are science questions related to each of these thematic areas. So one is dealing with the energy budget of sea ice, understanding the fluxes of energy from above and from below, and how those evolve over time. Number 2 is ice movement and deformation. How does the ice change? How is momentum transferred? Number 3 is clouds, precipitation, and aerosols. These are very important drivers for the system, for the energy in the system, and they're very highly uncertain. Biogeochemistry and ecosystems, again, a very important part, especially in the changing Arctic, where we have a change in the nature of the ice pack that has uncertain implications for biological systems and ecosystems. And number 5 is large-scale linkages. What does the detailed information that we get from a drifting observatory in the Central Arctic tell us about Pan-Arctic scales or even hemispheric scales? And this is a lot of the upscaling that will happen in coordination with modeling activities. So some of the kinds of measurements, you see some examples here, very detailed and coupled system. So atmospheric profiling, boundary layer structure and dynamics, atmospheric gases and aerosols and clouds and precipitation. Moving down towards the surface with surface energy budget, ice properties, ice thermodynamics, dynamics, and optics. Ocean and ice biogeochemical processes. We want to understand about leads and ocean surface. And of course, the ocean state, profiling, and dynamics. And a lot of these measurements will be made, as I said, at the central facility, and many distributed in space around that facility. So a recent implementation planning workshop we had has started to design some of that implementation. And so here's an example, if you can imagine, a cluster of measurements to provide that distributed network around the polar stern, which is listed in the center there. This is just a kind of conceptual diagram right now, but it's the starting point as we start to figure out how to couple the different subsystems at a variety of scales. So you can imagine that in the ocean or the ice or the atmosphere or the ecosystem, there's different scales that are of importance, different scales of variability. And so we're really thinking a lot about how best to design a structure that to capture the important variability that leads to the coupling. And so this variety of stations around the polar stern will have a variety of different objectives. Many of them will have, well, pretty much all of them, I guess, will have position very well measured so that we can understand the dynamics of the sea ice over a variety of scales, how deformation happens. A handful of the stations will be very intensive thermodynamic stations to understand all the different energetic fluxes that will lead to the thermodynamic state of the sea ice. Some stations will be for biogeochemical sampling, for example. And a lot of these will be tied together by some of these unmanned systems that can map across this space. So again, this design is kind of in progress, but this is where we're heading with in putting together this kind of science implementation. So I'm going to give you one slide here on just kind of an example of the kind of measurements and the system approach that we want to take with MOSAiC to understand how sea ice is evolving. And so this is an example actually from Shupe, which was another drifting station almost 20 years ago out in the sea ice in the Beaufort Sea. This is an example from January, and what we see is 2 weeks of data here. I hope people can see my pointer maybe. On the top panel we see in the vertical up to 5 kilometers, and over the course of this 2-week period we see those colors coming through are reflectivity from radar measurements. These are clouds drifting overhead. So we see a couple of events over the course of a couple weeks. These are kind of synoptic scale events that bring clouds. In the next panel down, we see the integrated ice and liquid water paths. This is the condensed amount of ice and liquid in those clouds. And this is a winter case, as I told you. This is, in early January, and temperatures are on the order of about minus 20 degrees, but we see significant amounts of liquid water in those clouds. These are important mixed phase clouds in the Arctic, something that we're really starting to learn about, but we have a lot to learn still. So we see that there are these periods of liquid water in the clouds coming through, and in the third panel down, we see the downwelling long-wave radiation. And when those liquid water clouds come through, we see dramatic jumps in the downwelling long wave of 40 to 70 watts per meter squared. Moving down again to the net atmospheric energy flux, we see that while there are some responses in the system, we still see important jumps in the total atmospheric energy flux at the surface related to those liquid water clouds. And those actually reflect in the surface temperature as well. So then if we jump to the bottom panel, this is actually profiles of temperature through the sea ice at the time. So the very top layer from 0 to 0.5 is the snow, and then we see the sea ice from 0 down to minus 2.2 about. And so these are temperature profiles through that sea ice, and we see that, in fact, when those liquid water clouds come through and have that radiative forcing on the surface, if you will, we see pulses of energy going down through the sea ice, through the snow and sea ice. And so that's changing the temperature of the sea ice. You can see kind of both the quick changes that are related to the events, but also a slow warming of the sea ice in the kind of upper layer around 0.5 meters depth. And a recent study by Ola Persson has actually looked at this case and suggested that this change in temperature structure in the sea ice is changing the conductive heat flux, which is plotted right above it, but it's also impacting the ice growth at the bottom of the ice, because as you change the amount of heat that can be conducted through that ice, you're going to change the ice growth rate. So this is a really nice example of this coupled system where we see clouds, and the clouds are being driven by kind of large-scale advection in the atmosphere, coupled with radiation, surface energy flux terms, temperatures structure in the sea ice, and ice growth. So a very coupled system approach, and these are the kinds of things that we're very interested in doing with MOSAiC. So to get on with some of the links then, how does MOSAiC fit in with the broader Arctic observing system? I have a series of slides here that just kind of shows a few of the important ways that MOSAiC can richen the observing system that we already have in place. So from the atmosphere perspective, MOSAiC would be a central Arctic node for a couple of important networks. So there's the ISO network. The map on the right there shows a bunch of different atmospheric observatories that kind of ring the coastline of the Arctic. So this would be a central Arctic node for that. Importantly as well, and I'll speak to it a little more later, the Department of Energy ARM program is putting a mobile facility onto the MOSAiC ship. And so this will be another node in the ARM network that includes nodes in Barrow and Iqaluit, Alaska, but also across the world to look at things like clouds and radiation drivers. So it's a nice central Arctic node to increase this kind of spatial coverage of those networks. There's also very important links with ongoing buoy programs. So I've listed a bunch of the buoys that we put out on a regular basis here on the right side of the slide. And these have been going out for many years, so we have very nice records. And the MOSAiC drift year will be a very nice opportunity to operate some of these buoys in this distributed network around the MOSAiC facility to both help put MOSAiC in the context of the longer-term observing that's been going on over the last few years, but also to richen those data sets to provide more of a detailed process understanding of what's happening in a lot of those measurements. So again, a very nice opportunity to enhance what's already going on. Of course, there'll be important links where we're building on a lot of the shorter-term process studies that have occurred over the past years. So ONR has had the nice MIZ and C-State projects. There's been some campaigns that I've been on, AXI and ASCOS, where we tried to do a lot of coupled system measurements for weeks at a time. So it'll really build on some of these experiences that we've had where, for example, MIZ deployed a constellation of autonomous sensors that I think would be a very nice model for how we deploy things around the MOSAiC facility. MOSAiC will also provide a nice in-ice counterpart for some of the biological studies that have been happening. RSALCA, DDO, the Pacific Arctic Group activities. I know there's interest in some of those communities for moving further north. And the MOSAiC drift, especially during the start of the drift, will be a nice opportunity to have a facility inside the ice that is very well equipped for biological studies. The Alfred Wegener Institute does a lot of biological studies using Polar Stern, and so certainly a lot of those activities are planned. This will provide a nice counterpart for a lot of the other biological activities that are happening generally further south. More so, I'll make another point about the biological activities is MOSAiC will also provide a nice opportunity to look at some of those in wintertime. And while most people say, the biology just shuts down in winter, there's this growing community. And myself not being a biologist, I'm just a listener here, but the community is really very interested in understanding what happens in the wintertime in the biological cycles. How dark is dark? That's one nice quote I heard from a meeting recently. So I think it's important to go out there and understand that. There's also important links to satellite measurements, of course. How well do we measure some of the important properties from satellites in the Central Arctic? I think that's a very open question. Certainly satellites are important for the aggregate scale measurements and the kind of long-term climatological view of the Arctic, but we really need to understand what we get out of these satellite measurements. And so ICESat-2 will be going up pretty soon, and the MOSAiC drift offers this really nice opportunity to have this drifting constellation of very intensive measurements. And you can imagine running ICESat in a mode where it takes views along the MOSAiC drift over the course of this full year, providing a data set that would be unlike any other as far as the ability to understand what ICESat-2 is really looking at with the sea ice, with deformation, with ice thickness, snow on sea ice, etc. So I think there's a lot of opportunities to provide some of the ground validation for satellite measurements that we just haven't had in the past. And lastly, MOSAiC's a really nice opportunity to help development of the observing system for the future. As an atmospheric scientist, I know we have a lot of gaps in our measurement abilities in the Central Arctic. We're not very good at autonomous measurements for the atmosphere, radiometers, ice up, for example. And so MOSAiC can really be a nice platform for helping to develop, test some of the instruments that we're going to need for the future to put out in a more autonomous fashion. Additionally, things like gliders in the ocean can really benefit from having people on site to develop proxies for converting the actual measurements into geophysical parameters. So there's a lot of important testing, development, and operations that can be done to help improve the kind of long-term viability of the Arctic observing system from a manned drifting station in the Central Arctic. So to bring things to a close here, just a little summary about MOSAiC into the future. So we're working on finalizing some of the plans. So the science plan is nearly complete. Implementation plan, we're trying to get that complete by the Arctic Science Summit Week. So we have some guiding documents. And then over the course of this coming year, there'll be additional proposals in the U.S., in EU, potentially in Asia. We'd like to have an open science meeting sometime in a year or so to really engage a broader community, all in preparation for a field deployment in September of 2019. And then my last slide here, the U.S. role. I think it's important, this is an IARPIC telephone call, so we should probably talk about the U.S. role a little bit. And I'd say that the international cooperation here presents this tremendous opportunity for us as a nation. The Germans are heavily invested. The Germans have put the Polar Stern on the table and are going through the planning activities of how to make that full year-long drift a possibility. But the U.S. has some really distinct capabilities and experiences. We have a lot of experience in the Central Arctic making a lot of these kind of measurements. And I think it's incumbent on us to show our leadership here. We can't really sit on the sidelines and expect to be able to get this amazing data set from the sidelines. So we really have a leadership role, I think, here. Department of Energy ARM program, has already contributed the mobile atmospheric facility to put on board the ship. So this is a very comprehensive suite of atmospheric measurements, very much a centerpiece of this activity. But we need more measurements. We need more contributions to really do the equivalent kinds of measurements in the sea ice and in the ocean, and to really ensure that we have the coupled system aspect of this covered. And so this is where I'd say we really need the interagency coordination that is possible through IARPC. And we need it in the near term. Some of the questions that I put forward here are, what will U.S. agencies contribute? Of course, those have to be proposal driven, but I think there's a little bit of more dialogue that needs to happen to really understand the scope of possibilities there. How will the different agencies' efforts be coordinated? What's the process for communities to access the support available? And then how will the U.S. come together to provide some of the larger support for things like logistics and resupply? The Germans are putting the ship out there, but we need to actually provide some support for things like fuel for that ship over the course of the year. So these are some really important questions, and I think IARPC is really the perfect entity to address some of these from the U.S. perspective. And really the guidance and the participation in this is something that needs to happen in the near term. Next year, I would say, is too late. The planning is happening right now, and the opportunity for U.S. engagement is right now. And so we need to be, I think, well-positioned to make investments and to rally our assets and our expertise in order to bring leadership to this activity. So with that, I'll say thanks for listening. The MOSAiC website is at the bottom of the page, and if you have any questions for myself, I'm happy to take those. Thanks.
Thanks, Matt, for that great presentation. We have time for a question or two.
So, Jeremy, this is Renee again.
Okay, go ahead, Renee.
I know the IARPC staff meetings take place once a month. Would that be an appropriate venue for the principals to address the question about coordinating agency contributions?
I can bring that up during the staff meeting to the principals, yes.
Great.
Sandy and I can do that, yes.
Fabulous, thanks.
All right, in the interest of time, we've got about 20 minutes left, so I think we should switch over and let